Isopropanol is one of the essentials in this world as it creates a lot of possibilities for the chemical industry. So isopropanol or isopropyl alcohol is derived from propylene gas from the crude oil. So how does it work actually? Today, our group is going to show the model on how crude oil can be turned into isopropanol.
Next, I will explain the petrochemical route for producing isopropanol or IPA from the crude oil. The process starts with the crude oil as the main feedstock. First, the crude oil enters the fractional distillation column where it is separated into a different fraction based on boiling points. In an actual refinery, this process also involves pumps, heaters and condenser. But for our model, we simplified the process unit. From this process, naphtha is selected for the next stage. The naphtha enters the steam cracking unit. In this unit, a very high temperature is used to break the hydrocarbons into smaller molecules, mainly propylene gas. Then the propylene reacts with the water in the hydration reactor under a high temperature and pressure in the presence of phosphoric acid catalyst to produce crude isopropyl alcohol. Then, lastly, the crude isopropyl alcohol undergoes purification using the azeotropic distillation to remove the water and impurities, producing a high purity isopropanol suitable for medical, electronic and sanitizing applications.
Good morning everyone. Today I will present about crude oil as feedstock source in the production of isopropanol. Crude oil is a natural fossil fuel mainly made up of hydrocarbons such as alkane, cycloalkane and aromatic compound, together with small amount of sulfur, nitrogen and oxygen compound. It is formed over millions of years from decomposition of dead plants and animals under high temperature and pressure beneath the Earth's surface. Crude oil is the most important raw materials in the petrochemical industry because it is used to produce fuels and many chemical products. However, crude oil cannot be used directly due to its very complex composition and impurities. Therefore, it must first undergo refining processes before it can be used in industrial application. During refining, crude oil is separated into different fractions according to their boiling point. These fractions include refinery gases, gasoline, naphtha, kerosene, diesel, and heavy residue. Each fraction has different properties and industrial uses. For example, gasoline is mainly used as transportation fuels, while diesel is commonly used in vehicles and industrial machinery. Among all the fractions produced, naphtha is especially important in production of isopropanol. Naphtha is used as the feedstock of steam cracking, which converts the hydrocarbon into light olefins such as ethane and propane. Propane is the key intermediate compound used to produce isopropanol through catalytic hydration. The composition and quality of crude oil can be vary depending on its sources. Some crude oil are lighter and produce higher amount of valuable fraction, while heavier crude oil contain larger hydrocarbon molecule and more impurities. Because of these differences, refineries need to adjust processing condition and operating method to maximize efficiency and produce yield. Overall, crude oil play a very important role in petrochemical industry and serve as starting feedstock for isopropanol in production. Through refining and further chemical processing, crude oil can be converted into valuable fuel and chemical intermediate used in many industrial applications.
After receiving crude oil from refineries, they are first preheated through heat exchanger and furnace to convert oil into a liquid vapor mixture. Inside the column, temperature controls everything. The bottom will remain extremely hot while the top is much cooler. Lighter hydrocarbon rise higher because they vaporize easily, while heavier component condense lower down. Based on boiling point, the column separates crude oil into useful fractions. Naphtha exits here. Naphtha later become essential for producing one of the building blocks for IPA. Other fractions are LPG, petrol, kerosene, diesel, gas oil, lubricating oil, and heavy residue named bitumen. Every layer of crude oil has a value. Nothing goes to waste.
Amir, after watching your presentation. I'm curious about the equipment used.
Well, I'm glad you asked. Using desalter remove salt content, Klaus equipment remove hydrogen sulfide, heat exchanger recover heats from product, furnace generating thermal heat for the process.
What about the condenser at the top?
That cools the rising vapors and turns them back into liquid fractions.
Wow! Then, the naphtha fraction can already be used for generating IPA?
Not yet. It must be categorized based off the boiling range and hydrocarbon composition such as light naphtha and heavy naphtha. Light naphtha contains lighter paraffins like pentane and hexane.
I don't understand. Why is that important?
Because lighter paraffins crack more easily, making light naphtha suitable for producing ethylene and propylene.
And the heavy naphtha?
Heavy naphtha contains heavier hydrocarbons and more aromatics, so it usually used for catalytic reforming, generating BTX and gasoline production by pushing higher octane value.
Then, I think lighter naphtha are more suitable for producing IPA, right?
Exactly! On to the next process.
Naphtha is a light hydrocarbon fraction obtained from the fractional distillation of crude oil, serves as primary feedstock for thermal cracking and a cornerstone of petrochemical industry that breaks a heavy hydrocarbon into valuable building blocks like propylene and ethylene. The process starts in the convection zone where naphtha at 50 degrees Celsius and 5.8 bar is mixed with steam to reduce coke formation and heated to 616 degrees Celsius without cracking. Cracking occurs in the radial zone at 600 to 900 using 80 burners, producing ethylene, propylene, butadiene, methane, and aromatics. The coil outlet temperature is controlled at 800 to 850 degrees Celsius and the product lives at 865 degrees Celsius before being rapidly quenched to 349 degrees Celsius in the transfer line exchanger TLE to stop further reactions. Coke formation is a major issue because it reduces heat transfer, lowers yield, and increases pressure drop, so periodic steam decoking is required. The cracked gas then undergoes several separation steps. After quenching, compression, acid gas removal, and drying, it enters a demethanizer to remove methane and hydrogen. A dethanizer separates C2 compounds while heavier C3 to C5 aromatic streams go to a depropanizer. The C3 fraction is purified in a C3 splitter with 120 to 200 trays to produce at least 99.5% polymer grade propylene. Finally, the C4 stream undergoes extractive distillation with NMP solvent to recover 99.7% pure butadiene, while the C5 fraction is processed to obtain aromatics such as benzene, toluene, and xylene.
Now, taking purified propylene from the steam cracking furnace, we are going to pass the propylene through a pipe to the hydration reactor, where the purified propylene is going to be reacted with water in a direct catalytic hydration process over solid phosphoric acid catalyst. This will turn propylene, also known as propene, into isopropyl alcohol. This reaction is carried out at 7,500 kilopascal or 25 to 40 atm. But this reaction will create a side product known as diisopropyl ether. This diisopropyl ether is considered as an impurity and a main impurity inside this reaction, where we are going to proceed to purification steps next.
Moving into topic 7, we receive the crude distillate from the hydration stage. While distillation is our primary tool for separation based on boiling points, ordinary fractional distillation alone cannot completely purify the stream. This is because isopropanol and water form a minimum boiling homogeneous azeotrope at which approximately 80 Celsius, where the liquid and vapor compositions become identical. To break this thermodynamic boundary, we implement azeotropic distillation. We introduce an entrainer solvent such as cyclohexane into the column to alter the relative volatilities of the components. The purification operates efficiently at atmospheric or reduced pressures between 80 to 85 Celsius. In our 3D model, this critical phase is represented by this light blue column. By employing this advanced system, we recover more than 99% of the isopropanol, achieving a final product purity of the 99.8% weight of isopropanol. This is represented by the yellow bottle in our model here, making it fully grade ready for electronic applications, pharmaceutical and medical.
Next, I will explain the industrial applications of isopropanol or IPA, which is the final product produced from this petrochemical route. So one of the major applications of isopropanol is in sanitizing and disinfecting products. IPA is commonly used in hand sanitizers, antiseptic wipes, and surface disinfectants because it can effectively kill microorganisms by damaging their proteins and cell membranes. During the COVID-19 pandemic, the demand of isopropanol increased significantly due to increased awareness of hygiene and sanitation. Besides that, isopropanol is also widely used in electronics cleaning. IPA is suitable for cleaning printed circuit boards, CPUs, camera sensors, and semiconductor devices because it evaporates quickly and leaves very minimal residue after use. This is very important because water or residue may damage sensitive electronic components. In actual industries, automated spraying systems and drying chambers are commonly used during electronic cleaning processes. In pharmaceutical and medical industries, high-purity IPA is commonly used as an antiseptic and sterilizing agent.
So firstly, the materials that we use for the 3D models is cardboard, and we use it for the structure and the base for our model. Next is we use plastic bottles for all of the processing units, as well as a box for the furnace. And then we use straws as the pipe to connect all of the processing units. And we also use marker pens and colored papers to design the model, as well as write the information below it.
In conclusion, this project successfully demonstrates how crude oil can be converted into isopropanol through several petrochemical processes such as fractional distillation, stream cracking, hydration, and purification. Although our model is simplified, but still it represents the important industrial process and process flow used in actual petrochemical plants. Overall, this project improved our understanding of petrochemical processing and the industrial applications of isopropanol. Thank you.